So it's lovely to be here. It's wonderful to be back in Malta. I really enjoyed the 8 months that I was here. And I want to thank the conference organizers, Irene and Peter and Josef and John, for inviting me, because it's been a wonderful conference so far. I'm going to talk about some work that I did with derangement graphs, and it's with a whole list of people. Bahman Ahmadi was a PhD student. Chris Godsill, maybe you've heard of him. Sam Jacques was an undergraduate student. Pablo Spiga in Milan. And another guy, Pham Tip, who's in Arizona, I do believe. So everybody's been enjoying the conference. We meet in this country. We're from all over the world, and we try to get to know each other and talk about our work. So I have an applied math problem. So what sets of languages should conference attendees speak so that there's the largest group of people so that any two can talk to each other? So here's my first example. We have a conference where the first person speaks Maltese and English, the next person Maltese and Italian, so they can talk in Maltese, and the last person English and Italian. These three people can all talk, and if anybody else wants to talk with them, they have to speak at least 2 of those 3 languages. Here's conference 2, where we have someone who speaks English Maltese, someone else English Latin, English Arabic, English French. Any 2 of these people can talk together because they both speak English. Okay, so being mathematicians, our practical problems, the first thing we do is add ridiculous restrictions to the problem. So what we're going to say is that there are only n possible languages. Everybody speaks exactly k of them, and no 2 people speak the same set of languages. And now what we want to do is figure out what's the largest conference we can make so that any 2 people can talk to each other. So what I'm really getting at is, what's the largest collection of k subsets? So the k subsets are different languages. We have a base set of size n. Those are all the languages in the world. And any 2 of the k subsets intersect, meaning any 2 people can communicate in that language that they both share. We've seen the answer to this a couple of times today. This is the famous Erdős-Colredó theorem. So provided that your n is bigger than 2k, which is a really mild restriction, because if your n is not bigger than 2k, it's all trivial. The largest conference you can have is n-1, choose k-1. And it's pretty easy to figure out what the setup is. It's all the sets that contain some common fixed element. Now, this is my favorite theorem. I like it so much that I wrote a book with Chris about it. There are many extensions and generalizations of this. For example, you can look at what's the largest set of t-intersecting sets. You can also ask what's the largest set system where they all intersect, but where you're not allowed to have the one where 1 is contained in every set. The theorem generalizes to lots of different objects. You can look at vector spaces over a finite field, and they intersect if their intersection has dimension larger than 1. You can look at separated sets, and so when's the largest collection of separating sets intersecting. And there's a whole world of people working on studying EKR for different objects. There's also many different proofs. We saw Catone's famous cycle proof this morning in one of the sessions. But I have my favorite proof, and I like the cycle proof very much, but it's maybe not my favorite. My favorite proof goes like this. I'm going to build a graph with the k subsets are the vertices. And what I'm going to do is put an edge between 2 vertices, like right here. I'm going to put the edge if they're not intersecting. And now what I'm looking for is the largest set of intersecting sets. So what I'm looking for is the largest co-clique in this graph. So independent sets, those are sets of vertices that they have no 2 edges, no 2 vertices have an edge in common. I prefer to call them co-cliques because the word independent has been really overused in math. And so you can see that, well, maybe you can't see. In blue, I have this co-clique. Those are all the sets that contain 1. So what I can do is I can take this problem of finding the largest set system, write it as a graph. Now I'm looking for the largest co-clique in a graph. And you can do this for anything that you want, any type of object that you're looking for an EKR type of theorem. You just put your objects down as your vertices, you make them adjacent if they're not intersecting, and then you go hunting for your largest co-clique. So here's an example that I really like. For a permutation group, so I'm going to have a group, it's a permutation group, so it comes equipped with an action, and I'm going to make the derangement graph. The derangement graph has the elements of the groups as its vertices, and then I look at this. If I have two vertices, H and G, they're going to be adjacent if H inverse G is a derangement. So a permutation is a derangement if it has no fixed points. So my vertices are not adjacent. It's easy to get when it's adjacent and not adjacent confused. So they're not adjacent if they're not a derangement. So this thing, H inverse G, is not a derangement. So it means it has a fixed point. So it maps I to I. And then when we look at G and H both map I to the same place. That's my idea of intersection for permutations. So now the question I want to answer is, what's the largest set of intersecting, in this sense, intersecting permutations in a group, a permutation group? That's exactly equivalent to asking, what's the largest co-clique in the derangement graph for the group? Okay. So here's an example of a couple of derangement graphs. So my group here is the cyclic group on 7 points. The derangement graph is not the most exciting because it's the complete graph. So if I take H inverse G of any of these, I'm going to get a cycle on 7 points, and it's not going to have any fixed points. The dihedral group has a slightly more exciting derangement graph, and this is the derangement graph for the symmetric group on 3 points. A couple quick facts about it. If we're looking at the group generated by a cycle, our derangement graph is just going to be the complete graph, and I can tell you exactly what all the largest independent sets are. If our group is generated by a single permutation, we can actually write the graph down as the complement of a circulant graph, and we can tell exactly what the circulant graph is by the cycle structure of our permutation. So here's my example. We have a group generated by this, and this has a cycle of length 3 and 2. If you look at this, every other one is going to have that 4 going to 5, 4 going to 5, 4 going to 5. So these guys are all intersecting. So those red lines aren't in my derangement graph. So it's the complement of, so the red lines are the circulant graph where for 2, and then the other types of edges are the 3. Those are here, we've got the 1, 2, 3, and we've got 1, 2, 3, so these guys are intersecting, so we don't have that edge. So the graph is really easy. It's the complement of a circulant graph, and I can write down exactly which circulant graph it is. If we have a direct product of groups, the internal direct product, the graph is just a direct product too. So there's a couple of easy things we can see about these derangement graphs right away. There's a little bit more going on here. I've defined my derangement graph to have edges where H inverse G is a derangement. Instead of having the edge where it's a derangement, I can have it be an edge where it's in a conjugacy class. So what I'm going to do, the vertices are the elements of the group. Now I've written it pi sigma. Pi inverse sigma is adjacent if this element is in the ith conjugacy class. This is an old familiar friend because this forms an association scheme, it's the conjugacy class scheme. So this is the pictures of the conjugacy, the classes in the conjugacy class scheme for the dihedral group. Now I'm not going to write down the definition of an association scheme. I'm just going to point out that what's going on here is this derangement graph is sitting in an association scheme, and an association scheme means that we have terrific algebra at our ready that we can use for all sorts of stuff. So this derangement graph is particularly nice, not just for EKR theorems, but because it belongs to this bigger family. Okay, so a co-clique in our derangement graph is a set of intersecting permutations. If I take the stabilizer of a point, so all the permutations that map 1 to 1, that's going to be a co-clique. Any coset of that is going to be a co-clique as well. So if we take all the permutations that map I to J, these are the cosets of the stabilizers of a point, and because that's hard to say, I call those canonical. Those are my canonical intersecting sets. Often in the literature, these are called trivial, but that's weird, right? Trivially intersecting can be confusing, so I call it canonically intersecting. If the canonically intersecting sets are the largest intersecting sets, we say our group has the EKR property. So this is a bound on the size of the largest intersecting permutations, and if the bound matches the size of the stabilizer of a point, we say that the group has the EKR property. Particularly if we're a transitive group, we know the size of a stabilizer of a point. So if we have a subgroup with a symmetric group, and the largest co-clique is the size of the group divided by n, then it has the EKR property. Not all groups have the EKR property. If you look at M20, which some people consider a Matthew group, some people don't. If you take the Matthew group on 22, Matthew group 22, and the stabilizer on 2 points, some people call that M20, that does not have the EKR property. You can find a co-clique that's larger than the stabilizer of a point. There's another group, Sim8. Normally you think of Sim8 permuting 8 points. I'm not going to do that because that's too easy. I'm going to look at Sim8 acting on ordered sets of size 4. So I'm going to take all the sets of size 4 from 1 to 8, put an order on them, and then the group Sim8 acts on them. In this case, the stabilizer of a point is the 24, the 4 factorial. But the set of all permutations that fix at least 5 points from a set of 6, it's also a clique. And I didn't work very hard to find this group because I based it on the largest T intersecting sets when your n is small. So Elsveda and Ketchatryan characterized exactly which are the largest T intersecting sets from an n set for all values of n and k and t. And these come out from that work, that there's nothing really creative in that. So I can find a whole lot of groups that don't have the EKR property. Okay, so I'm going to look at a couple more properties of my derangement graph, just in case you're not convinced that it's fantastic. It's actually, we've seen in some of the talks today the definition of a Cayley graph. So a Cayley graph, you have a group, and your vertices are elements of the group. And then you have a connection set. Your vertices are adjacent if H inverse G is in your connection set. It's a normal Cayley graph if your connection set is closed under the conjugation. So what we can see is that our derangement graph is a Cayley graph, and our connection set is just the set of all the derangements. The derangements are a union of conjugacy classes, so it's closed under conjugation. So our derangement graphs are normal Cayley graphs. The reason this is great is that we can now calculate our eigenvalues without too much trouble. So the eigenvalues of a graph are just the eigenvalues of the adjacency matrix. In the special case of a normal Cayley graph, we have a beautiful little formula that tells us what our eigenvalues are. So what we have to do is pull out an irreducible character for our group, and then we get, for each irreducible character, we get an eigenvalue by summing the value of the character over the elements in the connection set and dividing by the dimension of the character. So in this special case where we've got a normal Cayley graph, in some sense it's easy to write down what the eigenvalues are. Okay, so just to keep with this easy theme, if I use the trivial character, when I evaluate it on my group elements, I will just get 1, and so what I get is the size of the derangements is one of my eigenvalues, which is good because that's my degree, and if I didn't have that there, it'd be kind of worrying. So if we look at a Frobenius group, we can actually write down the spectrum of the derangement graph for any Frobenius group. We get n minus 1 with multiplicity k, and -1 with multiplicity n minus 1 times k. And just looking at those eigenvalues, you can tell exactly what your graph is, right? It's going to be, because we've got the n minus 1, so it's going to be the complete graph, and it's k copies of the complete graph. So when we pull out any Frobenius group, I can tell you exactly what all of the maximum independent sets are without doing any work. Another example is PGL2Q. Just for example, this is a group that the characters are completely understood and they're written down. I can go through and calculate all my eigenvalues without any trouble. So the reason I care so much about eigenvalues isn't just that it's an interesting property of your graph. But I can also put it into the Hoffman bound. I feel like maybe I've jumped. I'll get to the Hoffman bound in a second. Okay, I'm going to head there. I'm going to calculate my eigenvalues to stick them into the Hoffman bound and get a bound on my co-cliques, and everything will be awesome. So let's see. If I have a subgroup of the symmetric group, I have this function, the fix. So the fix just takes a group element and says how many elements are fixed by that group. So your group's acting on a set, so how many elements in the set are fixed by that group element. And it's called the permutation character. Using Burnside's lemma, I can calculate this, the sum of the fix over the group elements, number of orbits. If my group is transitive, the number of orbits I have is just 1. If I'm 2 transitive, I can calculate this. This is the orbits on the pairs, and I have 2 orbits on the pairs. One orbit is where I have 1, 1, 2, 2. Because it's 2 transitive, it's 1 transitive, so that's 1 orbit. And then where the other orbit is all the other pairs. And because it's 2 transitive, it's just a single orbit. So what I'm going to do is take this permutation character, just the fix of G, and I'm going to make up a new character. If my group is 2 transitive, I can look at this character, where I take the fix minus 1. When I take the inner product of that character with itself, I can just expand it out. Using these 2 facts that I just figured out, I get that the inner product with itself is just equal to 1. What that tells me is that this is an irreducible character. Now, in general, it's a character for any group, but only when your group is 2 transitive is it an irreducible character. So in the case where I have a 2 transitive group, I've got a lovely little character sitting right here, ready for me to use to get an eigenvalue. So if I'm 2 transitive, that character I defined as irreducible. I'm going to use it to get an eigenvalue. So I can take it and put it into my formula. So I'm going to get an eigenvalue by taking the value of the character over everything in my connection sets, over all the derangements, and dividing it by the dimension. So the dimension of this character is n minus 1. And my connection set is the set of all derangements. It's easy to calculate how many fixed points the derangements have. There's 0, minus 1. It's -1 for everybody. And I have this eigenvalue sitting right here. So whenever my group is 2 transitive, I have this, d, the number of derangements, divided by n minus 1 and the negative. That's going to be an eigenvalue. So I've calculated 2 eigenvalues of my derangement graph, the degree, and this one right here, the degree divided by n minus 1, negative. Okay, so this is exciting to me because I'm going to pull out Hoffman's ratio bound. Hoffman's bound tells me that if I have a regular graph, I can get a bound on the size of the co-cliques by taking the number of vertices, dividing by this thing. So d is the degree, which is the largest eigenvalue, and tau is my smallest eigenvalue. And I have a big if here. I don't know if you can see it, but it's in bold to emphasize that it's a big if. So if that eigenvalue I pulled out is actually the least eigenvalue, then I can go ahead and put it in my formula, and I get this lovely little number right here. So in the case when my group is 2 transitive, if this is guaranteed to be an eigenvalue, if it happens to be the least, I get the exact right bound that I want. So whenever this eigenvalue is the least for 2 transitive group, that 2 transitive group is necessarily going to be EKR. We also have a couple other properties going on here, that if equality holds, so if this bound holds with equality, which we would have because we can do the stabilizers of a point, if we have a characteristic vector for maximum co-clique, so the characteristic vector is just a vector the length of the group, 1 if that group element is in the set, and 0 if it's not. If I take that characteristic vector, and all I'm doing here is subtracting off a multiple of the all ones vector, and this just makes it orthogonal to the all ones vector. So this new vector right here is going to be an eigenvector for tau. And I can actually use this in some cases to get a characterization of all the sets that are maximum co-cliques. We can also do a weighted version of this bound. So I did this bound for the adjacency matrix of the graph. So where d is the largest eigenvalue and tau is my smallest eigenvalue, I can do that not just for the adjacency matrix, but I can weight my edges and get a weighted matrix and still calculate the eigenvalues and use this bound. Okay, so the big theorem that I have is that Spiga and Tip and I proved that every two-transitive group has the EKR property, which was sort of nice because we thought that was what would happen. It's not the case that every two-transitive group has that magic eigenvalue as its least. So we had to do a little bit of work to get this. Our proof actually uses the classification of finite simple groups, which sort of makes me a little bit sad because I'd like to be able to just use the two-transitive property rather than have to use the classification, but it actually worked, so I'll take it. What we did is we went through each type of two-transitive group and showed that the size of the maximum co-clique in the graph was this number here that we want. We needed two sort of helpful lemmas that I won't go through in too much detail. I'll just point out that if your group, this should be the group, not the graph. If the group has a sharply transitive subgroup, so a sharply transitive subgroup is exactly equivalent to a clique of size n in your graph. So if you have a sharply transitive subgroup, then automatically your group's going to have the EKR property. That's just the clique co-clique bound, and it's nice and easy. The other property we have is that if we have a group H in Sim n that's two-transitive and has the EKR property, and if H is a subgroup of a bigger group, then the bigger group also has the EKR property. They have to be acting on the same set, but if the little guy has the EKR property, the big guy has it too. What this means is putting these two together is that we didn't have to look at all the two-transitive groups. We could actually just look at the minimal normal subgroups of the almost simple two-transitive type. So what we did is we pulled out a little table of them. So we found the table of all the groups we cared about and went through and checked each one, which I won't make you do with me, but I'll just point out sort of how it works. These ones in red, these ones are all finite, so GAP did them for us. So I think Pablo and I put them into GAP, maybe we went to get a cappuccino, and when we came back, they were all good. The alternating group was done, actually the first group to be done was the symmetric group, and then my grad student and I did the alternating group. The alternating group is tricksy in that if you ask a group theorist what are the irreducible characters for the symmetric group, they'll laugh at you and say, that's all known, everybody knows what it is. But when we actually go to calculate the eigenvalues, you can do any one group, but to show that this eigenvalue we're holding on to is actually the smallest of all of them is sort of tricky, that it's hard to show that you don't get a character sort of later on that's smaller than this one we're holding on to. And so I think Chris Godsill and I found a workaround when we did a proof for Sim n, and David Ellis has a lovely proof of showing that that eigenvalue we care about is the least eigenvalue. His is super clever in that it uses nothing harder than what you teach in your first year linear algebra. And when you see his proof, you're just like, oh, I can't believe I didn't think of that. It's really nice. So I've copied, so some of these here, these ones in blue, we could calculate some of the eigenvalues, but we had the same problem that we couldn't calculate all of them because there's infinitely many. But we used David Ellis's trick of showing that once we have the degree, the one we think is the smallest, the rest all have to be strictly smaller in absolute value. And then there are these ones. Can you see the purple colors? This is the Higman-Sims, the symplectic group, the projective special unitary groups. These ones were a little bit more of a problem because when we calculated out their eigenvalues, especially for small groups, the magic eigenvalue that we want to be the smallest wasn't actually the smallest. So we had to be more clever. So I'll show you what we did for the Higman-Sims group. What we did is we made a weighted adjacency matrix. And my weighting is sort of ridiculous. So the Higman-Sigs group has 5 conjugacy classes that are derangements. I'm lazy, I'm gonna weight all the derangements the same. What I did is I took a bunch of the conjugacy classes that looked big and big, I weighted them 1, and the rest of the other classes I weighted at 0. So what I did is I actually took the whole derangement graph, threw out a whole big bunch of edges, which you'd think would make your independent sets bigger, but it didn't. It stayed the same. So with this ridiculous weighting, we're able to use the Hoffman's bound, and it worked out just fine, that it has the EKR property. The other group, this was sort of my favorite. I'm not actually going to go into this in too much detail. It's one of these things I spent a long time calculating, but nobody wants to know the details of it. PSU, the Projective Special Unitary Group 3Q, its character table, you can't read it, and it's probably for the best. But its character table is known in a sense, but it's sort of difficult to calculate things. And when I first started working with this with different values of Q, I put it in the computer and I was like, what are the eigenvalues? And it turns out that the magic eigenvalue, it turns out it's this guy right here, this character. The eigenvalue that I want to be the smallest wasn't always the smallest. So I tried doing linear combinations. But what I found is that as I picked linear combinations on the conjugacy classes, I sometimes got different characters giving me the least eigenvalue. So there's two conjugacy classes of derangements. I want to weight these conjugacy classes so that these eigenvalues, so this is the character, the permutation one, the fixed -1. This is the character I like. This is another character. What I was able to do is weight the conjugacy classes so these two guys both had the same least eigenvalue for the graph. And it was one of these things I was looking at originally and I thought there's no hope. I've got 3 equations, 2 unknowns, it's hopeless. But it wasn't, it actually worked. So I was pretty pleased. Okay, so that was our proof that your two transitive groups always have the EKR property. So if you're two transitive, the largest intersecting set of permutations is the obvious one, where you take all the elements that map I to J. So the next question, so that's the bound. That's the bound in the EKR theorem. Once you do the bound, the next thing you want to do is the characterization. So the next question is, what exactly are all the maximum co-cliques? Can we characterize all the maximum independent sets in these graphs? Okay, so what we've defined is the strict EKR property. The strict EKR property is if the only maximum co-cliques are these canonical co-cliques. And it's not true that all two transitive graphs have the strict EKR property. I can pull out an example right here, the projective general linear group 3Q, which is the example you're all thinking about, right? This one does not have the strict EKR property. But Pablo and I worked on this, and we were able to show, obviously, the stabilizer of a point is going to be a maximum co-clique. The stabilizer of a hyperplane is also a maximum co-clique. And what we actually did was show that these are all the possibilities, and they're cosets. So it was a bit of work, a fair bit of calculation to show that you couldn't have anything else, but we used this eigenvalue approach and to work it out. Okay, so just going back a step, we have the eigenvalues of our Cayley graph can be calculated this way, where we take our character, evaluate it on the connection set, and divide by the degree, where we have an irreducible representation. We can do projections to these eigenspaces. So this character gives me the eigenvalue, but I can actually write down the projection to the eigenspace. I'm going to be air quotes around eigenspace, but this is my projection. So E chi, the GH entry, is the value of the character on H inverse G, and then normalized. I'm putting, well, let's say it this way. We call the image of this projection the chi module. I'm calling it the chi module rather than the eigenspace because it's sort of pedantic, but you could get two different irreducible representations giving you the same eigenvalue, and then the eigenspace is both the modules together. But this guy is a chi, I call it the chi, it's maybe not a great name, but it's the module corresponding to chi. It's a G module because it's closed under the action of G. And so it's part of the eigenspace, but it may not be the entire eigenspace. So I'm also going to hold on to some special vectors, V, I, J. these are the characteristic vectors of my canonical intersecting permutations. So these are the characteristic vectors for all the permutations that map I to J. Now, if I'm too transitive, these are guaranteed to be maximum co-cliques. And so there's two facts about these. If my group is too transitive, then these vectors are in the chi module that I defined. So these are the characteristic vectors for all the things going from I to J. And I do this little thing here. All I'm doing is making it orthogonal to the all ones vector. Another property that we have is that if I take these vectors, and I don't use all of them, I and J, so it's all permutations that map I to J, I'm not going to take all the ones that include N. So I only go part way up. That turns out to be a basis, which is sort of nice. And that's easy to prove because you can just do a calculation. Okay, so what I have in my head is I know that if my group is too transitive, it has the EKR property. So I know the size of the largest co-clique. I know that all my canonical guys, so all the permutations that map I to J, have that maximal size. And the question is there anything else? Are there any other co-cliques sitting in this graph that could be the same size? So what I'm going to do is pretend S is a co-clique of maximum size, and VS is going to be the characteristic vector of it. Now, if it turns out that this VS is in the chi module, then this VS is a linear combination of these VIJs. And that's sort of the property that Pablo and I used when we were looking at the projective general linear group, is we were able to show that if we have any co-clique, the characteristic vectors in the right module, and then we looked at these linear combinations and showed that the linear combination is either trivial, so it's a VIJ, or the linear combination gives you the stabilizer of a hyperplane. So every minimal normal subgroup that I've looked at of almost simple two transitive type has the property that the maximum co-cliques are all in the chi module. So I kind of think what's going on is that when we're too transitive, we're not always strictly EKR, but I think we're actually always sitting in this module. And I can prove it for all of the littlest guys, but I'm not really sure yet how to prove it for the guys in between. So this leaves me with some questions. So does every two transitive group have the property that every maximum co-clique is in the chi module? I kind of think so, but I don't know. And if it is in the chi module, then that says that any maximum co-clique is a linear combination of these VIJs. So what can I say if I have a vector, it's a characteristic vector, and it's a linear combination of this? Can I start getting information about the structure of co-cliques if I know that they have to be formed by looking at linear combinations of these vectors? So that's an open question. And I also have some further work that I'm interested in. If my work is all focused on the two transitive groups, but there's lots of groups out there that are lovely and nice and not too transitive. If I have any group and any group element, the fix of G is still a character, fix of G minus 1 is still a character. What I lose is that it's not irreducible anymore. So the eigenvalues are not going to work. And looking at examples of transitive but not too transitive groups, the eigenvalues don't work for finding the maximum co-cliques. But if I'm transitive, I can write this character as an induced character from the trivial on the stabilizer, and I induce it up to the group. So it's still a nice character, and I still have a module. And the module may not be irreducible or indecomposable, but maybe I can still use it for looking at the EKR theorem. So maybe rather than using the eigenvalues, I can look more at the modules and say that the characteristic vector has to sit in the module, and the module is spanned by a set, and so it has to be a linear combination of these vectors, and maybe get at the characterization that way. So the last thing I'm going to say is my future work is I'd like to use this approach for families of transitive groups and see if I can get anything with that. That's it.
Are there any questions for Karen?
Thanks very much for a fascinating talk. It may be something I've missed or it may be a failure of my imagination, but I'm just wondering what, if anything, happens in the case of abelian groups. Is it all just simplified, or the case of it's all trivial?
It is all trivial, yeah. I forget what the answer is, but sorry. I'm pretty sure it is all trivial, and I forget right now what the answer is, but I wrote a paper with Bauman Amadi when he was doing his PhD with me, where we just did sort of the easy groups like Frobenius and abelian, and it just, I'm pretty sure all we did was the obvious thing, and it just worked out easily.
Okay, so the two transitive groups are all primitive, but M20 is primitive as well. So this EKR property for primitive groups obviously stops somewhere in between two transitive and primitive. Any idea where?
No idea. There's sort of, it'd be nice to do the characterization for two transitive and then start looking at other groups. I would start with like low rank groups, but in terms of outside the two transitive, I don't have a lot yet. So there's lots of interesting stuff to work on.
Has this approach been successful with higher order EKR, with T intersection and?
Do you mean permutations or sets? Because for sets, Wilson's proof of the T-intersecting sets uses a weighted adjacency matrix in the eigenvalues. For permutations, I've not been brave enough. I would think, once I have a PhD student again, I think I might get them to try and do two intersecting elements, like two intersecting subgroups for, say, just the symmetric group, and try to do a weighted adjacency matrix like Wilson. But like Wilson's proof writes down this beautiful matrix and says it works, and his work is, it's hard and it's really good. So for permutations, you'd probably be able to get it with a weighted adjacency matrix, but you'd have to figure out what the weightings are and calculate your eigenvalues, which I don't know. I think it's feasible, but hard.
Any more questions? We thank her. Yes. No, don't thank her yet.
What you've just talked about, hasn't this been done already by Alice Friedkut and Pilpel, the intersection problem? For insufficiently large, okay, but